Hi, this is MEC 3503, and the multi-component device that this report analyzes is a wind turbine. A wind turbine is a renewable energy device that converts the wind's kinetic energy into usable electrical energy that provides electricity to cities and homes all over the world without producing greenhouse gases. Wind turbines come in a large variety of shapes and sizes and generate various amounts of electricity.
The first segment we are going to be looking at is the wind turbine tower. These towers are approximately 100 meters in height and sometimes even larger. They tend to have a wider diameter base and narrow as they reach the top. It's made up of multiple segments in general cases, and there's three main types of towers: steel towers, concrete towers, and hybrid towers. Today we'll be focusing on the steel tower. So the manufacturing process is as follows. It starts with CNC cutting, followed by bending, which leads to the milling and drilling portion, which then it goes to welding, and followed by non-destructive testing, and lastly, the coating. The CNC cutting, basically in this phase, it cuts the raw sheets into the desired dimensions. The dimensions are accounted for and material loss, so it's usually cut into slightly larger than the required dimensions, and it cuts into the profile of what is needed. So for the flanges, it's a circular profile, and then the raw sheets are cut into rectangles, which are then bent into the desired profile. So again, bending and beveling. The flat sheets are bent into a sort of a circular profile here, in which creates the cylindrical segments of the tower. Milling and drilling is mostly applied on the flange. So basically, each flange has multiple holes all around, which is the holes for the bolts, which basically two flanges are bolted together. And the milling is sort of creating a lip on both sides of the flange in which the segment is welded on. So it creates a nice clean finish at the end. The welding. So once your rectangular sheets are bent into the circular profile, the ends are then welded together to create one full segment. And once that is done, the each flange is welded onto each side of the segment. So there, on each segment, there's a flange on both sides, which then are the flanges are then connected together during installation. The non-destructive testing, it's gone through some ultrasonic testing, penetrant testing, extreme weather testing, and in the inspection phase, it goes through multiple inspections to make sure it's correct dimensions and tolerances. Because once these are transported, it's very hard to bring back. So it's got to make sure everything is good before it leaves the plant. And they just got to make sure that the flange holes are aligned. That's the biggest thing, so they can be bolted together. Basically, these are always in wide field, so it can go. It can be under extreme weather conditions, so they needs to be tested for that and absorb shocks and stuff from nearby communities. It is then coated, sandblasting, anti-corrosive coating, and paint. This basically just protects it for years and years, so they don't have to take it back down and treat it for rust and such. So in the future, there's many manufacturers that are looking to shift towards wooden towers because they're lightweight, easier to transport, and they're easier to manufacture, and they're more cost effective. Basically, the wood is taken on site and it is assembled there. But if you want to stick to steel, I can see that in the future, maybe in 2050, they can start 3D printing these in entirety, which will be easier to manufacture as there will be way less steps. And once the material is fed, it just 3D prints into the desired shape and dimensions.
Hi, I'm K.R. Patel. Let's talk about third component of the wind turbine, the main shaft. Main shaft is the primary device that transfers torque from rotor to the rest of the drivetrain. It also supports the weight of the rotors, and it's mainly made of steel. The manufacturing process for main shaft involves 6 steps. The production of steel stock, machining using lathe, milling and drilling, heat treatment, surface finish, and the inspection at the final. Step 1 is to produce a steel roll bar using the molten metal. Ladle furnace is used to fine tune the temperature and chemical composition. A carbon content is achieved using the vacuum degassing process. A continuous casting or bottom fed die casting is used depending on the shaft diameter. Once the millet is extracted using either of the process, it is processed from the rolling to achieve the smaller diameter shaft, and for the larger diameter shaft, it is processed using computerized press. The large steel bar stock is then loaded onto a large CNC lathe. Using the turning and cutting using the carbide tool, the final geography of the shaft is achieved. For the next step, a finer features such as pass-through hole mill holes for demounting and the key grooves are achieved using drilling and milling process. The shaft, now finalized, is reheated to 1200 degrees centigrade in a quench annealing furnace, followed by rapid cooling in oil or water. The material is tempered around 600 degrees centigrade to ensure the material structure is in accordance with specifications. Shafts are now transported to cooling bed and prepared for further processing. The fifth step of the process is the surface finish. A short blasting process is used to remove the surface contaminant and minor impurities. The final step is inspection. Dimensions are checked and recorded. Measurement of surface roughness is done. A microstructure is analyzed using ultrasonic testing and electromagnetic testing. Some other form of non-destructive testing is performed to ensure the quality of produced shaft. The future of shaft manufacturing is a composite material such as carbon fiber. An increase in torsional strength by 8.5% along with weight reduction of up to 60% leads to increase of strength to weight ratio by 300%, which indicates the carbon epoxy shaft can successfully replace the steel shaft. The future manufacturing of composite materials involves two primary steps: production of carbon fiber using polymerization and spool winding. Multiple carbon fiber spools are used in a step 2 that involves filament winding to produce the shaft. Thank you.
The purpose of the blades is to convert the linear motion of the wind to the rotating motion of an axle. The blades are typically 25 to 70 meters long, with the longest manufactured to this date being 107 meters. They typically weigh 11 to 25 tons and upwards. The blades must be lightweight and strong. High stiffness is required such that the blades do not wobble in high winds, allowing them to have clearance and not hit the tower. They must be resistant to high cycle fatigue. Currently, most turbine blades are made of fiberglass embedded in a thermoset resin matrix. The most common manufacturing method for the turbine blades is vacuum-assisted resin transfer molding. A composite mold is laid out on the shown form. A nozzle is used to apply gel coat to the surface of the mold. The gel coat is an epoxy-based thermal setting coat that provides a finish for the blades and facilitates the removal from the mold. Fiberglass weaves are then rolled into place to smoothly cover the mold surface. Towards the base, balsa wood or polymer foam are sandwiched in between the fiberglass layers to ensure greater structural integrity. The mold is then covered by a silicone vacuum bag, which is sealed with tape. There are holes in the vacuum bag to which tubes are mounted. Through these tubes, air is taken out to maintain a pressure of less than 1 bar, while resin is forced inwards. The thermoset resin is then heated to cure it. So today, the turbine blades are made with tons of thermosets. At the end of life, thermosets cannot be recycled and thus are disposed of. With the use of improved thermoplastics in the future, we will be able to recycle these blades. Thermoplastics do not need to be heated to cure, therefore also being more energy efficient to manufacture. In the future, we are pushing towards larger wind turbines which generate more energy. With an increase in size, the weight of the blade will have greater impact on the efficiency. To maximize the lightness of the blades, carbon fiber will be the primary material. So by 2050, we will see the turbine blades manufactured through the pultrusion of carbon fiber. Individual strands of carbon fibers will be pulled off spools to form sheets. These strands of carbon fiber are passed through a resin like the one mentioned prior to form the composite. They will then be placed in a mold and allowed to solidify into the desired shape.
Component 4 is a gearbox. A gearbox is connected to a low-speed input shaft from the outside rotor, and it couples that shaft through a series of gears to a high-speed output shaft that is connected to the generator. A function of the gearbox is to increase the slow rotation of the input shaft to the speed that is high enough to power the electrical generator. Looking at a common GE 1.5 megawatt wind turbine, the input shaft rotates at approximately 20 revolutions per minute, and the output shaft must rotate at approximately 1,500 revolutions per minute in order to generate electricity. A common ratio for a wind turbine gearbox is approximately 90 to 1. So if the input shaft was rotating at 20 RPM, with a 90-to-1 ratio, it would produce a rotational speed of approximately 1800 RPM at the output shaft. Gearbox manufacturing process. There are many different ways in which gears can be manufactured depending on their size and function. The first way is called hobbing. Hobbing progressively generates gear teeth using a helically fluted cutting tool called a hob. The hob and gear blank rotate as the hob is fed axially across the face of the blank. This is the most common method for producing spur gears or helical gears. Shaping. Shaping consists of rotating workpiece in contact with a reciprocating cutter. The cutter can vary between a pinion-shaped cutter, a multi-tooth rack-shaped cutter, or a single-point cutter. For large turbine gears, it is likely that a rack or single-point cutter would be used. Rack-shaped cutters have approximately 6 to 12 teeth that reciprocate into the gear blank, and a single-point cutter has 1 tooth. The cutter reciprocates until the required tooth depth is achieved, then the gear rotates to create the next tooth. Milling. Milling is a machining process that uses the relative motion between a rotating multi-edge cutter and a workpiece to generate the gear shape. The cutter usually mills each gear tooth space individually. And lastly is gashing. Gashing generally used to produce large, coarse-pitched spur, bevel, or helical gears, either internal or external. A rotating cutter plunges into the gear blank for rapid metal removal. After machining, gears usually require heat treatment in order to increase the hardness of the gear, and after heat treatment, gears usually require finishing to remove any distortions that occur during the machining or heat treatment process. Credible vision for gearboxes in 2050. Gearboxes are the weakest part of a wind turbine. The planetary gearbox design must be changed in order for wind turbines to be efficient and provide an environmental and economic benefit. A credible vision for a wind turbine gearbox in 2050 is that the gearbox will no longer exist in the turbine. There are 2 companies in Germany and Norway that have already produced gearless direct drive wind turbines. The basis that these turbines function on is instead of increasing the rotational speed of the shaft in order to produce electricity from a 4 or 6 pole generator, they would increase the number of poles of the generator, which would allow them to reduce the rotational speed of the output shaft. Having enough poles on the generator will simply eliminate the need for a gearbox. Manufacturing of gearboxes in 2050. Manufacturing of wind turbine gearboxes in 2050 will be extremely different than today because first and foremost, wind turbine gearboxes will probably not exist in that year because of the new idea of direct drive wind turbines. For smaller wind turbines in residential areas, I can see gearbox being manufactured from additive manufacturing processes like 3D printing or other processes that may result in a more wear-resistant gear. Thank you, and if anyone has any questions, we'll answer them now.